There is a pinprick of red light at the edge of the observable universe. It should not exist. It is too bright, too compact, too early, a blazing point of energy shining out of a cosmos that, by every model we have, had not yet had time to produce it. It does not emit X-rays the way it should. It does not vary the way it should. And when astronomers point the most powerful space telescope in human history directly at it, what they see rewrites the first chapter of everything. What is it? Where did it come from? And why does its very existence suggest that the laws of physics, as we understand them, may be missing something we have never once imagined? For 30 years, scientists dreamed of a machine that could see the beginning of time. Not metaphorically, literally, or rather, observationally. A telescope so powerful, so precisely engineered, and so perfectly positioned in the cold dark of deep space that it could capture photons of light that left their sources when the universe was barely a few 100 million years old, when the cosmos was still warm, still young, still chaotic with the first furious blooms of structure. The idea was audacious and technically terrifying in equal measure. Build a primary mirror 6, 5 meters across from 18 individually polished beryllium segments coated in a film of gold 100 nanometers thick. Fold the entire structure inside a rocket, launch it 5 million kilometers from Earth to a gravitationally stable parking point called the second Lagrange point, and then, over the course of 344 single point of failure deployment steps, unfurl it perfectly, without a single error, in the silent vacuum of space, the James Webb Space Telescope launched on Christmas Day, 2021. At the time of its launch, no engineering project in the history of humanity had required so many sequential steps to all succeed perfectly. If any one of those 344 steps had failed, one misaligned mirror segment, one jammed sunshield layer, one sticky actuator, the telescope would have been unreachable for repair, silent and cold in the dark, 1.5 million kilometers from the nearest human hand. It did not fail. Every step succeeded. And when the first images arrived in July 2022, they stopped people cold. The images were not merely pretty. They were not the kind of pictures you tape to a refrigerator out of aesthetic appreciation. They were epistemological detonations, documents of places and times so remote that processing their implications required a kind of mental recalibration that most people, scientists included, were not fully prepared for. The cosmic cliffs image, a jagged edge of glowing gas and newborn stars in the Carina Nebula, 7,600 light-years away, was the kind of picture that makes you suddenly, viscerally aware that you are a creature on a small rock orbiting an ordinary star. The deep field image, capturing thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length, represented light that had been travelling toward us for billions of years. But the images were only the beginning. What Webb was truly designed for, its real purpose, the mission around which decades of planning, billions of dollars, and the careers of thousands of scientists had been organised, was spectroscopy, not photography. The ability to split incoming light into its constituent wavelengths, to read the chemical fingerprints baked into starlight, the way a forensic chemist reads evidence from a crime scene, and to do this for objects so far away that the light arriving at Webb's detectors had been stretched by the expansion of the universe to the point where what was once ultraviolet radiation had been redshifted all the way into the infrared. This was Webb's superpower, the ability to look in infrared wavelengths, to see through the dust and gas that blocked earlier telescopes, to read the chemistry of the first galaxies, the first stars, the first black holes. The plan, as astronomers understood it going into the Webb era, was fairly straightforward. The standard model of cosmology, a robust mathematically elegant framework known as lambda CDM, or lambda cold dark matter, made very specific predictions about the early universe. It predicted that the first galaxies would form slowly, assembling themselves from tiny clumps of gas and dark matter over hundreds of millions of years, growing gradually, building their stellar populations incrementally. It predicted that the first billion years of cosmic time would be a relatively quiet epoch, a slow kindling of structure in an otherwise dark and undifferentiated void. It predicted, in summary, that the universe we would find at redshift 6, 7, 8, 9, corresponding to epochs when the cosmos was only 700, 600, 500 and 400 million years old, respectively, would be young-looking, sparse, primitive. What Webb found instead was something else entirely, and the strangest thing it found, the discovery that has generated more scientific arguments, more competing papers, more sleepless nights for cosmologists, and more genuine, open-mouthed bewilderment than anything else in the telescope's now 3-year observing history, does not have a grand scientific name. It does not go by a Latin designation or an alphanumeric catalogue identifier. The astronomy community, with uncharacteristic informality, calls them little red dots. The first time anyone saw a little red dot, they thought it was a data artifact. This is not unusual in observational astronomy. When a detector is imaging objects at the absolute edge of its sensitivity, when the signal is so faint that the photon counts involved could be counted on 2 human hands per exposure, systematic errors and instrumental noise can masquerade as real astronomical signal. You see a point of red light at some improbable redshift, and your first instinct, professionally trained and appropriately cautious, is to question your instrument before you question the universe. The universe has had 8 billion years to construct itself along well-understood physical lines. Your detector has had at best 5 years on orbit, but the little red dots kept appearing. By March 2024, when a team led by Jorit Mati and Rohan Naidu published their landmark analysis of JWST survey data, the catalogue of confirmed and candidate little red dots had grown to a number large enough to rule out instrumental artifacts with cold mathematical certainty. Then 341 confirmed little red dots had been identified across multiple independent JWST surveys, found in different fields of sky, detected by different instruments, confirmed by different spectroscopic programs. They were not a glitch. They were real, and they were extraordinary. To understand why, you need to appreciate what they look like in the data, and why that appearance is so deeply strange. A little red dot is, as the name implies, small and red. In the infrared images taken by Webb's NOCM instrument, they appear as compact, point-like sources, objects so physically tiny that even Webb's magnificent angular resolution can barely resolve their internal structure. Their radii average around 500 light-years, with many measuring less than 150 light-years across. For context, the Milky Way galaxy has a radius of roughly 52,000 light-years. A typical little red dot is approximately 2% of the radius of our galaxy. It is a pinprick, a mote, a barely there flicker of light at redshifts of 5, 6, 7, 8 and beyond, placing these objects at distances corresponding to epochs when the universe was less than 1.3 billion years old. But they are not faint. That is the first contradiction. Despite their extraordinary compactness, little red dots are luminous, in some cases ferociously so. The object catalogued as A2744-45924, located in the Abell 2744 galaxy cluster field, is the most optically luminous little red dot yet identified. It blazes with the light output of billions of stars, packed into a space barely wider than the distance between the Sun and the nearest few hundred neighbouring stellar systems. Something is generating an enormous amount of energy inside a very small volume. Something is burning or accreting or collapsing with a ferocity that defies easy categorization. Their spectral shape is the second contradiction. When Webb's NIRSpec spectrograph disperses the light from a little red dot into its component wavelengths, astronomers receive a fingerprint that should be familiar but is not. In the ultraviolet part of their rest frame spectrum, the short wavelength end before the light was stretched by cosmic expansion, little red dots appear blue, reasonably blue, star-forming galaxy blue in fact. But in the optical part of the rest frame spectrum, they become ferociously, deeply red. Not the gentle red of a cool old star, an aggressive, steep, rising redness that climbs with wavelength in a way that suggests large amounts of gas, dust and hot ionized plasma surrounding an intensely energetic central source. This V-shaped spectrum, blue in the UV, pivoting sharply to red in the optical, is unique. Astronomers had never seen it before Webb. It appears in little red dot after little red dot with a consistency so striking that it serves as a kind of signature. When you see the V, you know you are looking at a little red dot. But nobody, as of the moment the first 100 examples had been catalogued, could tell you with certainty what was producing it. The third contradiction is perhaps the most troubling from a purely theoretical standpoint. Approximately 80% of little red dots that have been observed with spectroscopy show what astronomers call broad emission lines, specifically broad hydrogen emission lines, the Balmer series, produced by electrons in hydrogen atoms dropping from higher to lower energy states. Broad emission lines in a compact, energetic object are one of the most reliable indicators in all of observational astronomy for the presence of a supermassive black hole actively devouring material. The broadening occurs because the gas orbiting the black hole is moving at enormous velocities. Velocities so high that the Doppler effect smears out what would otherwise be a sharp spectral spike into a wide rounded peak. In the case of little red dots, the gas in their cores is moving at roughly 900 kilometers per second. That is not a mild indication of accretion, that is a screaming declaration of it, so far, so comprehensible. Supermassive black holes at the centres of young galaxies, feeding voraciously on surrounding gas and generating enormous luminosities, are a known and well-studied phenomenon. They are called quasars, or active galactic nuclei, and they were among the first objects that Webb was expected to study in the early universe. If the little red dots were simply a new population of early active galactic nuclei, exotic but understood in principle, they would be a notable discovery, a worthy entry in the scientific literature, a chapter in a textbook someday. But little red dots are not behaving like active galactic nuclei, not the way we understand active galactic nuclei to behave, and that is where the real problem begins. When matter falls into a supermassive black hole, it does not go quietly. The accretion disk, the swirling pancake of superheated gas spiraling inward, becomes one of the most energetic environments in the universe. It generates X-rays, copious, powerful, hard X-rays, because the gas in the innermost regions of the disk is heated to temperatures of tens of millions of degrees. Every known active galactic nucleus at every redshift emits X-rays. It is considered a defining characteristic. It is the smoking gun. A supermassive black hole actively accreting material, producing the kind of luminosity that the broad emission lines in little red dots imply, should be blasting out enough X-ray radiation to be detectable with current space telescopes. The little red dots are almost completely silent in X-rays, stacking analyses, where astronomers combine the X-ray data from dozens or hundreds of little red dot positions to amplify any faint signal, have produced detections so marginal that they are essentially consistent with zero. There is no X-ray scream, there is no X-ray whisper. For objects that their own optical spectra insist should be among the most energetically active phenomena in the early universe, the little red dots are, in the domain of high-energy radiation, almost mute. And then there is the variability problem. Active galactic nuclei vary, they flicker, they pulse. The accretion process is inherently turbulent. Clumps of gas fall in at different rates. The disk wobbles, the magnetic fields threading through the infalling material fluctuate. And all of this produces measurable variability in the luminosity of known quasars and active galactic nuclei on timescales of days to months to years. When you monitor a known quasar over time, you see it change, sometimes dramatically. Little red dots, when monitored across multiple epochs of Webb observation, show almost no variability. They are eerily, inexplicably stable. Here then is the central problem of the little red dots, stated with the precision it deserves. Their broad emission lines say, this is a supermassive black hole, accreting furiously, surrounded by gas moving at nearly 0 kilometers per second. Their X-ray silence says, this is not an active galactic nucleus as we know them. Their photometric stability says, whatever this is, it is not fluctuating like an accretion disk. And their V-shaped spectra say, nothing we have ever studied before looks quite like this. Three open questions now hang in the air. What are they? What is generating their extraordinary energy? And why does their very existence, in the numbers and at the distances where Webb finds them, challenge every simulation we have ever run of the early universe? Before we can begin to understand what the little red dots are, we have to confront a problem that is logistically more alarming than the problem of their nature. There are too many of them. This sounds like an odd complaint. Astronomers do not generally protest the existence of too many objects. But the little red dot abundance problem is not a matter of aesthetic preference. It is a quantitative crisis. When you count the number of little red dots that Webb has found across its various survey programs and compare that number to the predictions of the Lambda CDM standard model of cosmology, the model that predicted in advance how many quasars, galaxies, and active galactic nuclei of various types should exist at various redshifts, you do not find a small discrepancy. You do not find a 10% shortfall or a factor of 2 excess that might be explained by tweaking a parameter here or adjusting an assumption there. You find a number that exceeds theoretical predictions by roughly 3 orders of magnitude. Little red dots, as catalogued by Webb, appear to be roughly 0 times more common in the early universe than any model of galaxy formation or black hole growth had anticipated. 1,000 times more common, let that land. Not we underestimated slightly, not. There are more than expected. 1,000 times more common. If you ran the most sophisticated cosmological simulation available before Webb launched, using the best physics, the best computers, and the best empirically calibrated models of star formation and black hole growth, and you then asked your simulation to predict how many little red dot type objects should exist in a given volume of the early universe, the answer you would get is a number roughly 3 powers of 10 smaller than what Webb actually observes. This is not a small adjustment to a parameter. This is a foundational failure of prediction. Now, at this point, the scientifically careful among you will note, correctly, that abundance alone is not enough to condemn a physical model. You might ask, could the model be off for reasons that have nothing to do with new physics? Could the identification criteria for little red dots be too broad, accidentally sweeping in objects that are not truly the same phenomenon? Could the survey selection effects, the biases inherent in observing only certain patches of sky with certain wavelength sensitivities, inflate the apparent number? Could the photometric redshift estimates for at least some little red dots be wrong, placing them at high redshifts when they are actually nearby objects misidentified by their colours? These are precisely the questions that the community has been working through since 2024, with rigorous spectroscopic follow-up programs that have systematically confirmed the high redshift nature of little red dot after little red dot. The Rubies survey, Red Unknowns, Bright Infrared Extragalactic survey, led by Anna de Graaf and Gabriel Brammer, spent hundreds of hours of precious Webb observing time using NearSpec to obtain spectroscopic confirmations of the brightest and reddest distant sources in 2 independent survey fields. The results were unambiguous. The little red dots are real, they are at the redshifts their photometry indicated, and they are genuinely abundant. But the abundance problem, as disturbing as it is only the surface layer of a deeper crisis. Because underneath the question of how many little red dots exist lies a question that strikes at the core of black hole physics itself. How massive are the black holes inside them? The answer, when it finally came in from spectroscopic analyses, caused at least one team leader to, by their own account, step away from their computer and spend 20 minutes staring at a wall. Supermassive black holes grow by accreting mass from their surroundings. They begin, according to all pre-Webb models of black holes seeding in the early universe, as relatively modest seeds, the remnants of the first massive stars, collapsing to form black holes of perhaps 100 to 1,000 solar masses. These seed black holes then grow over time by consuming gas, merging with other black holes and gradually building themselves up to the millions or billions of solar masses that characterize the supermassive black holes we observe in galactic centers today. This growth process takes time. It obeys, at some fundamental level, the Eddington limit, a physical constraint that caps the rate at which a black hole can accrete material before the radiation pressure of its own emissions pushes that material back out. An Eddington-limited black hole can, at maximum, roughly double in mass every roughly 45 million years. The little red dots have black holes that appear, from the dynamics of the gas swirling around them, to be 10 million to 1 billion solar masses in size. At redshifts of 7, 8 and 9, the universe was between 550 and 700 million years old. The arithmetic is unforgiving. To reach a billion solar masses from a 100 solar mass seed in 700 million years at Eddington-limited growth is not merely difficult. It is, under conventional models, physically impossible. The time simply does not exist. You cannot grow a black hole that massive, that fast, by any mechanism that standard physics unambiguously permits. The specific object that brought this home most powerfully was Kuiper's LRDZ9, confirmed in work published in 2025. This little red dot sits at a redshift of 9288, making it the most distant active galactic nucleus ever spectroscopically confirmed. The universe, when its light left it, was approximately 535 million years old. Its broad emission lines indicate a black hole already hundreds of millions of solar masses in size, sitting inside a galaxy so compact it could fit within a region a few hundred light-years across, surrounded by dense ionized gas that simultaneously explains its redness and its X-ray silence. By any conventional model of structure formation, a supermassive black hole of this mass has no business existing at this epoch. The universe had not had time to grow it. This is what astronomers have called the early black hole formation problem. And it is, to my mind, one of the most genuinely disorienting puzzles in all of modern physics, because it is not a problem of subtle measurement uncertainty or marginal statistical significance. It is a problem of fundamental arithmetic applied to fundamental physics, and the arithmetic does not close. But the abundance problem and the mass problem, as shocking as they are, still do not quite capture the full depth of the strangeness. Because there is a third layer, a third dimension of inexplicability, that has emerged from the most detailed spectroscopic analyses of individual little red dots. Their gas is impossible too, the Balmer break. This is a feature in the spectrum of hydrogen-emitting gas, a sharp discontinuity at a wavelength of 364, 6 nanometers, that appears when a substantial column of relatively cool hydrogen gas absorbs the shorter wavelength photons being emitted by something hot behind it. In the spectra of normal galaxies, a Balmer break occurs because starlight from hot young stars is partially absorbed by the cooler stellar atmospheres of the stars themselves and by the surrounding interstellar medium. The depth of the break tells you something about the age of the stellar population, the star formation history, and the amount of gas present. In little red dots, the Balmer break is enormous, deeper than it has any right to be, deeper than any combination of stellar populations, dust configurations, and interstellar media can plausibly produce within the AGN framework. The break is so pronounced, the drop in flux across the Balmer discontinuity so steep, that to explain it with stars alone requires a population of old, evolved stellar systems whose age is inconsistent with a universe barely 500 million years old. You cannot have old stars in a young universe. The universe has not been operating long enough to produce them. Something in the gas around these objects is absorbing light with a ferocity that standard models of AGN physics struggle to explain. The gas is extraordinarily dense enough to act as a kind of shroud that simultaneously produces the enormous Balmer break, traps the X-rays that the accreting central engine should be producing, and stabilizes the system against the variability that would otherwise betray its turbulent inner nature. This is a feature that does not fit cleanly into any pre-Webb taxonomy of astronomical objects. It is not a galaxy. It is not a quasar as previously understood. It is not simply an active galactic nucleus in an early primitive state. It is something that, when the first credible theoretical models arrived, pushed at least 3 independent teams of theorists toward explanations so exotic that publishing them required a particular kind of professional courage. What are 3 possible identities that theorists have proposed for the little red dots? The answers, when they arrived, were more extreme than almost anyone had anticipated, and one of them, if correct, would mean that we have just witnessed for the first time in observational history an object that theory had predicted must exist but had never, in 70 years of searching, been seen. Every good scientific mystery generates theories in proportion to its difficulty. An easy mystery attracts 1 or 2 candidate explanations. A genuinely hard mystery attracts many, because when the standard tools fail, imagination is all that is left. The little red dots, in the 3 years since their discovery, have attracted theories that range from the plausibly exotic to the outright revolutionary, and tracking the evolution of that theoretical landscape tells you something important about how science actually works when it is confronted with something genuinely new. The first serious theoretical framework to gain traction was the AGN in a shroud model. This proposal, developed and refined by multiple groups including Kohei Inayoshi and Roberto Maiolino, begins with the observation that all the apparent contradictions of the little red dots, the X-ray silence, the stability, the enormous Balmer break, might be explained if the central accreting black hole is surrounded by a shroud of gas so extraordinarily dense that it qualifies as what physicists call Compton thick. In a Compton thick environment, the column density of intervening material is high enough that even energetic X-ray photons are unable to escape without being scattered, absorbed, and re-emitted as lower energy radiation. The X-rays are not absent, they are imprisoned. They cannot reach us because the gas cloud surrounding the black hole is effectively opaque to them. The dense gas also explains the Balmer break. Gas at the right temperature and density, surrounding an intense ionizing source, will produce exactly the deep absorption signatures observed. And the stability is explained by the fact that the extreme compactness and density of the surrounding medium smooths out the natural variability of the accretion process. This model is internally consistent and has been validated to varying degrees by detailed radiative transfer calculations. The work published in Nature in January 2026 by Rusakov and colleagues, placing little red dots specifically in the framework of young supermassive black holes embedded in dense ionized cocoons, is its most sophisticated instantiation. A supermassive black hole seed, the model argues, in the earliest phases of its growth, before it has had time to blow away its birth environment with the radiation pressure of its own accretion, would be exactly this: compact, energetically powerful, X-ray quiet, Balmer break deep. A cosmic cocoon phase in the infancy of the universe's most massive black holes, but this model does not fully solve the mass problem. A cocoon around a growing black hole explains the observational properties. It does not explain where the black hole mass came from in the first place, or how it grew to hundreds of millions of solar masses in a universe younger than the Milky Way's thick disk. The second theoretical framework is more exotic, and, in the view of several researchers, I find persuasive or intellectually compelling. This is the quasi-star hypothesis. A quasi-star, first proposed theoretically by Mitchell Bagelman and colleagues in the 2000s, is an object that, as far as can be determined, has never been directly observed before Webb. The concept is this: in the very early universe, before metals, elements heavier than hydrogen and helium, had been synthesized in significant quantities, the cooling mechanisms available to a collapsing cloud of primordial gas were far less efficient than in later epochs. Gas clouds that begin to collapse in such a metal-poor environment cannot radiate away their gravitational energy as efficiently, which means they cannot fragment into the relatively small stellar mass pieces that characterize modern star formation. Instead, they can collapse more monolithically, building up enormous central concentrations of gas that grow to masses far exceeding what any modern stellar physics would predict as stable. In a quasi-star, the central region becomes so massive and hot that a black hole forms inside it. But instead of disrupting the star or halting the collapse, the black hole sits at the heart of a vast, gravitationally bound gaseous envelope, accreting the surrounding gas at super Eddington rates, because the radiative pressure from the accretion is dissipated within the opaque stellar envelope, rather than being able to escape and push back on the infalling material. The black hole grows rapidly, fed by a reservoir of gas orders of magnitude larger than it could accrete in the open. The system is, in essence, a factory for rapid black hole growth, one that sidesteps the Eddington limit not by violating it, but by burying the accreting source inside a structure large enough that the radiation cannot escape to exert back pressure. A quasi-star is simultaneously a star and a black hole incubator. It would be compact. Most of its luminosity comes from the central accretion, not from distributed nuclear burning across a stellar volume. It would be red because the photons generated deep inside must traverse enormous optical depths before escaping, emerging only at the lowest energies the envelope permits. It would be stable because the variability of the central accretion is hidden behind the gaseous blanket of the stellar envelope. And it would be X-ray quiet, for precisely the same reason the photons are trapped and thermalized long before they could escape as hard radiation. Begelman and Dexter published a detailed model of little red dots as late-stage quasi-stars in 2026, presenting it as a candidate explanation for the full suite of observed properties. Their work was not without caveats. The predicted infrared emission from a quasi-star envelope does not perfectly match every observed little red dot spectrum, but it represents a serious, physically motivated attempt to explain objects whose properties otherwise defy easy categorization. And then there is the third theory. The one that, when I first encountered it, required me to sit with it for rather longer than the others. In July 2025, Devesh Nandal and Abraham Loeb being one of the most prolific and, it must be said, most provocative theoretical astrophysicists working today, published a paper in the Astrophysical Journal proposing that at least a substantial fraction of little red dots are not black holes at all. They are not quasi-stars. They are not AGN in cocoons. They are population 3 stars. Population 3 stars are, in the cosmological sense, the original inhabitants of the universe. They are the first generation of stars, formed from primordial gas composed almost entirely of hydrogen and helium, the only elements produced in significant quantities in the minutes after the Big Bang. They have never been directly observed. We know they must have existed because the universe they created, the metals in your blood, the oxygen in your lungs, the carbon in your DNA, could only have been forged in stellar interiors and explosive deaths. Population 3 stars are the foundational generation, the first forge masters. They formed the first heavy elements and scattered them into the intergalactic medium when they died, seeding all subsequent generations of stars and galaxies with the chemical raw materials of complexity. But nobody has ever seen one. They burned out billions of years ago, before any telescope existed to observe them. We have searched for their signatures in the spectra of ancient metal poor stars, in the chemical abundances of extremely old globular clusters, and in the spectral fingerprints of the most distant quasars. We have never found a clean, unambiguous detection, until Nandal and Loeb argue the little red dots. The specific class of population 3 star they invoke is not the modest solar mass object of popular imagination. They propose supermassive population 3 stars, objects of perhaps 1 million solar masses, formed in the extraordinary conditions of the earliest epoch of cosmic structure, when collapsing primordial gas clouds could accumulate to densities and masses far exceeding anything possible in a metal-enriched universe. Such a star, if it could form, and theoretical models have suggested it is possible, if challenging, would be extraordinarily short-lived. A million solar mass star would exhaust its nuclear fuel in thousands of years rather than millions. It would spend most of its lifetime in the last few thousand years before collapse, blazing with a surface luminosity and spectral energy distribution that, When Nandel and Loeb ran the theoretical models, reproduced the V-shaped UV to optical spectrum of little red dots with remarkable fidelity. The Balmer break depth matched, the compactness matched, the luminosity range matched, the absence of X-rays matched, because a stellar photosphere, even an extraordinarily hot one, does not produce the hard X-ray emission characteristic of an accretion disk. The supermassive population 3-star model would, if correct, represent the first direct detection of the universe's first stellar generation. Not a hint, not an indirect chemical signature, but an actual direct observation of the objects themselves, caught in the final thousands of years of their brief, spectacular existences. I find this possibility, as I have found very few things in my years covering science, genuinely moving. If the little red dots are dying first-generation stars, then what Webb is showing us, in those pinpricks of red light scattered across the early universe, is not an anomaly to be explained away. It is a last look, the universe's oldest fires, burning their last before going dark. But the theoretical landscape does not converge on a single answer. As of the most recent observations available, no single model explains all little red dots, and the community remains deeply, productively divided. What the three theories share is this: all of them require the early universe to be capable of producing objects far more massive, far more rapidly, and under far more extreme conditions than the standard model of cosmology had predicted. Whether those objects are black holes, cocoons, quasi-stars, or supermassive population 3 stars, their existence implies that the first billion years of cosmic time were not a quiet, gradual kindling of structure. They were a conflagration. There is a particular kind of scientific experience that has no formal name in any textbook, but that every working scientist who has spent years on a difficult problem will recognize immediately when it is described to them. It is the experience of sitting at a table with your colleagues, looking at numbers that you have worked for years to obtain, and watching the universe refuse, definitively and politely, to do what you had hoped it would do. Wendy Friedman had that experience on March 13, 2024, in a conference room at the University of Chicago. Friedman is one of the most decorated observational cosmologists of the past 4 decades. She led the Hubble Space Telescope's key project on the extragalactic distance scale, a multi-year observational campaign that, in 2001, produced the first precision measurement of the Hubble constant using Cepheid variable stars, arriving at a value of 72 km per second per megaparsec. She has spent the intervening quarter-century refining that measurement, arguing that the systematic errors in cosmological distance measurements are larger and more treacherous than the field generally acknowledges, and cautioning, with a persistence that has occasionally annoyed her colleagues, that certainty about the Hubble tension is premature until those errors are fully understood. The Hubble tension is the other crisis that Webb was supposed to resolve. It is in some ways an even more fundamental rupture in cosmology than the little red dots, though it does not carry the same visceral strangeness. The tension goes like this. When you measure the current expansion rate of the universe using Cepheid stars and Type Ia supernovae, the method developed by Henrietta Leavitt, refined by Hubble, and brought to extraordinary precision by modern instruments, you get a value of approximately 73 km per second per megaparsec. This means that for every megaparsec of distance, every 26 million light-years between two objects, those objects are flying apart at 73 km per second due to the expansion of space itself. When you independently predict the current expansion rate of the universe using the cosmic microwave background, the leftover thermal radiation from the Big Bang, mapped with extraordinary precision by the Planck satellite, and used with Einstein's equations to model how the universe should have evolved from its earliest moments to today, you get a value of 4 km per second per megaparsec. The universe, according to the physics of its infancy, should be expanding at 67.4. According to the rulers and standard candles of its present, it is expanding at 73. The difference is 8. 4%. In isolation, that sounds small, but both measurements are made with precisions of 1 to 2%, which means the discrepancy is roughly 5 standard deviations. In particle physics, a 5 sigma discrepancy is the threshold for declaring a new discovery. In cosmology, it suggests either a systematic error of extraordinary persistence in one or both methods, or a genuine gap in our physical model of the universe. Some ingredient, some effect, some new physics operating in the early cosmos that we have never included in our equations, that has left the universe expanding faster than theory predicts. The stakes are not trivial if the Hubble tension is real. If it reflects genuine missing physics rather than measurement error, then the standard cosmological model is incomplete. The model that cosmologists have spent 50 years constructing, testing, and refining, that has passed every observational test thrown at it from the cosmic microwave background to galaxy clustering to gravitational lensing, is missing something, and that something would need to be a new component of the universe, a new form of energy or matter operating at some point in cosmic history, whose effects have been invisible to every experiment yet conducted. This is what Wendy Friedman has been trying to determine. Her strategy, developed in the years leading up to Webb, was to use multiple independent distance indicators rather than relying solely on Cepheids. If different methods, different types of stars used as distance markers, calibrated differently, living in different galactic environments, all agree on the same value of the Hubble constant, that convergence is powerful evidence that the measurement is correct. If they disagree, that disagreement is diagnostic. It points toward the systematic error that is distorting at least one of them. She secured Webb telescope time to observe 11 nearby galaxies using 3 types of distance indicators: Cepheid variable stars, TRGB stars, tip of the red giant branch, the point in stellar evolution at which a red giant's helium core ignites, producing a remarkably standard brightness that can be used as a cosmological ruler, and JAGB stars, J-region asymptotic giant branch, carbon-rich giants emitting strongly in the infrared, accessible in detail only with Webb's sensitivity. Each method was analysed independently by a separate sub-team, with the results obscured from the others by a random numerical offset, until the day they all sat down together, the Ides of March 2024, a table in Chicago. The offsets removed for a few minutes, looking at the preliminary combined result, it appeared that the Hubble tension had gone away. All 3 methods were giving values close to 67 or 68, consistent with the Planck prediction, inconsistent with Rias's 73. Sort of jaw-dropping, Friedman would later recall to Quanta magazine. The years of careful, painstaking work had paid off. The systematic errors in the Cepheid method she had always suspected were real, and now, with independent methods confirming the lower value, she appeared to have the evidence to demonstrate it. Then the team went back into the data to write up the results, and the universe declined to cooperate. In the TRGB analysis, the error bars were larger than expected. Reducing them required including more red giant stars, and when the team did so, the derived distances shifted subtly, but enough to push the resulting Hubble constant upward. In the Cepheid analysis, they found something worse. In approximately half the Cepheids in their sample, the correction for stellar crowding. The adjustment needed to account for the fact that other nearby stars inflate the apparent brightness of a Cepheid had been applied twice, a computational error. When they fixed it, the Cepheid-based Hubble constant rose toward Rias's value. It brought us more into agreement with Adam, Friedman acknowledged, which ought to make him a little happier. The tension was resurrected, at the table where it had for a few minutes seemed to die. When the team finally published their analysis, it presented 3 separate Hubble constant values. The JAGB method gave 67.96 km per second per megaparsec, in near-perfect agreement with the Planck prediction. The TRGB method gave 69.85, and the Cepheids gave 72.45, with an uncertainty range stretching from 69 to 73, depending on how certain stellar population assumptions were made. The methods disagreed with each other. An average combining all 3 yielded 69.96. with a 4% uncertainty that overlapped with both the theoretical prediction and Rias's team's higher value, resolving nothing, not from lack of effort. Adam Rias, reviewing the preprint, expressed concern about the small supernova sample used to calibrate the distances, arguing it could introduce its own biases. He stood by his team's result of 73, 0 kilometers per second per megaparsec, a value they had confirmed independently using Webb data. The Hubble tension remains unresolved. Both teams are among the most careful, most rigorous in the field. Both have access to the same telescope. Both are getting different answers. Saul Perlmutter, Nobel laureate, one of the discoverers of dark energy, put it plainly when he assessed the situation. The Hubble constant has such a long and glorious tradition of being an impossible decades-long problem. He was not being grim. He was being precise. What strikes me about Wendy Friedman's experience in that Chicago conference room is not the frustration of watching a potential resolution dissolve back into ambiguity. It is something subtler. It is the intellectual honesty that her entire scientific career represents. She has spent 20 years as the skeptic, the voice of caution, the researcher who consistently pointed to the systematic errors that others preferred not to discuss. She did not simply want the Hubble tension to go away. She wanted to understand whether it was real or artificial, and when her own analysis, after years of preparation, seemed briefly to say it was artificial, and then, on closer inspection, turned out to be underpowered, with internal disagreements that matched precisely the systematic error she had always worried about, she did not bury the result. She published it, discrepancies and all. That is how science works when it is working well, not with triumphant announcements. With honest, incremental, sometimes frustrating accumulation of evidence, and with the professional courage to say, we are not there yet. To understand why the Hubble tension matters at civilizational scale, why it is not merely a technical dispute between measurement teams, but a crack in the foundation of our deepest model of reality, you need to appreciate what the Lambda CDM model actually is, and what it means for that model to be wrong. Lambda CDM is, without overstatement, the most successful large-scale physical theory in human history. It predicts, from a handful of parameters, the structure of the observable universe across scales ranging from the fluctuations in the cosmic microwave background. Temperature variations of 1 part in 100,000 imprinted on the sky in the first 380 years after the Big Bang, to the largest structures in the universe, the web of filaments and voids and galaxy clusters that spans billions of light years. It predicts the abundance of hydrogen and helium in the universe. It predicts the clustering statistics of galaxies. It predicts the way matter bends light along the line of sight to distant quasars. In every testable domain it is correct. Every testable domain except one. The current expansion rate, the lambda in Lambda CDM, stands for the cosmological constant. Einstein's original greatest blunder, reintroduced by theorists after the 1998 discovery by Rias and Perlmutter's teams that the expansion of the universe is accelerating. Something is driving the universe apart faster and faster as time goes on. Something with a negative pressure that acts like an anti-gravitational force permeating all of space. That something was named dark energy. Its physical nature remains completely unknown. It is described by lambda, a constant in Einstein's field equations, whose value can be measured but not explained from first principles. It represents our single most conspicuous acknowledgement that we do not understand the energy budget of the vacuum. The CDM stands for cold dark matter, the invisible, non-interacting, gravitationally dominant component that accounts for approximately 27% of the total energy content of the universe. Dark matter neither emits light nor absorbs it. It does not interact with the electromagnetic force. Its only manifest effect is gravitational. We infer its existence from the rotation curves of galaxies, the mass-to-light ratios of galaxy clusters, the statistics of gravitational lensing, and the pattern of temperature fluctuations in the cosmic microwave background. In every one of these independent lines of evidence, the data demand more mass than visible matter can provide, and in every one of them, the data are consistent with a cold, collisionless component of dark matter, whose distribution follows the same gravitational equations as ordinary matter. We have never detected a dark matter particle directly. No experiment, in 4 decades of increasingly sensitive searches, has found a signal, and yet everything we know about the universe depends on dark matter being real. So, lambda CDM contains 2 ingredients, dark energy and dark matter, that together account for roughly 95% of the total energy matter content of the universe, and for which we have not the faintest direct evidence about their physical nature. And now, in addition to these 2 deep unknowns, the model's most precisely testable prediction, the current expansion rate of the universe, disagrees by 5 standard deviations with the most direct observational measurement of that rate. When physicists say the Hubble tension might indicate new physics, they mean something specific. The tension lives between 2 different epochs of cosmic time, the early universe, as described by the cosmic microwave background, and the late universe, as measured by our local distance ladder. If the tension is real, something happened between those 2 epochs to alter the expansion history in a way that lambda CDM does not account for. That something would have to leave its mark in the equations of general relativity, in the energy budget of the universe, in the physics of the dark sector. The most popular candidate is early dark energy, a hypothetical form of vacuum energy that contributed significantly to the expansion rate of the universe in the early cosmos, before recombination, and then faded away, leaving behind only the faint echo of a slightly faster expansion that persists to the present day. Early dark energy models can in principle reconcile the Planck-predicted 67, 4 with the locally measured 73 by giving the early universe an extra push that the standard lambda CDM framework does not include. But these models have their own problems. They modify the early universe in ways that generally make other cosmological observables slightly worse, not better, trading one discrepancy for others. There is a second candidate, primordial magnetic fields, generated in the extremely early universe before or during inflation, could have left imprints in the plasma of the early cosmos and altered the physics of recombination in ways that shift the inferred expansion rate. This is a more speculative proposal, but has the virtue of connecting the Hubble tension to a physical mechanism that was theoretically motivated for independent reasons. And there is a third possibility, which the most cautious cosmologists still take seriously: systematic errors in the distance ladder that have, despite decades of effort, not yet been fully identified and corrected. The debate between Rias and Friedman is, at its core, about precisely this possibility. If the Cepheid-based distance measurements are biased high by some unrecognized source of error, crowding, metallicity effects, dust in galactic disks, then the local value of the Hubble constant would be artificially inflated, and the tension would be artificial. The James Webb Space Telescope was supposed to settle this. Its infrared sensitivity, its spatial resolution, its ability to pierce the dusty galactic environments where Cepheids live. These were precisely the tools needed to evaluate the systematic errors in the distance ladder with the precision required. Rias's team used Webb to check their Cepheid distances and found confirmation. Friedman's team used Webb and found mixed results. 3 years into the Webb era, the tension remains. It has, if anything, deepened, and now, with the little red dots added to the picture, astronomers are confronting a universe that is, in at least 2 independent ways, failing to behave as the standard model predicts. The Hubble tension says the universe is expanding faster than theory allows. The little red dot abundance problem says the early universe produced massive objects far faster than theory allows. These are not obviously connected. They could have separate causes. But the simultaneous failure of lambda CDM predictions in 2 independent domains is difficult to dismiss as coincidence. Some theorists have speculated that a model capable of explaining both anomalies might in fact explain the mechanism by which the early universe produced so many massive black holes and quasi-stars so quickly. If the expansion rate in the first billion years was slightly faster than lambda CDM predicts, structure formation would proceed differently. Density fluctuations in the primordial gas would be amplified in ways that could produce more massive, more rapidly collapsing objects. The same new physics that resolves the Hubble tension might be precisely the new physics that explains the little red dots. Whether this convergence reflects a genuine unified explanation or merely the attractive danger of searching for patterns in noise remains to be seen. But the possibility that the two crises point to the same missing ingredient has become one of the most actively pursued ideas in theoretical cosmology, and it represents, to my thinking, the most exciting frontier in physics since the discovery of dark energy itself. There are now 4 open threads pulling the science forward simultaneously: the identity of the little red dots, the cause of the Hubble tension, the nature of dark matter, and the physical origin of dark energy. Any one of these would be a transformative discovery. That all 4 are simultaneously in play in the same telescopic era is either the worst moment in cosmological history to be a theorist or the best. Before we declare the standard model broken, we need to be rigorously honest about what it still gets right. This is not a formality. It is a necessary act of intellectual hygiene, because the most dangerous mistake in science is to abandon a working model prematurely in the excitement of an anomaly that has not yet been fully explored. The history of physics is littered with premature obituaries for robust theories, and it would be a disservice to the genuine complexity of the current situation to ignore the many ways in which lambda CDM continues to triumph. The cosmic microwave background power spectrum, the detailed pattern of temperature fluctuations in the 2.725 Kelvin thermal bath that permeates all of space and represents the electromagnetic echo of the universe at 380 Zuzan years of age, is described by lambda CDM to a precision that remains one of the most stunning achievements of theoretical physics. The Planck satellite's 9-year mission mapped these fluctuations with an angular resolution of approximately 5 arc minutes and a temperature sensitivity of a few millionths of a Kelvin, finding that the lambda CDM model, with 6 free parameters, accounts for every acoustic peak, every trough, every subtle correlation in the data, across angular scales ranging from the full sky to patches smaller than a single degree. The model was not tuned to fit this data after the fact. The broad predictions were made before Planck launched, and the observations confirmed them. Big Bang nucleosynthesis is another triumph. In the first 3 minutes after the Big Bang, the universe was hot and dense enough for nuclear reactions to proceed at cosmologically significant rates, and the theory of primordial nucleosynthesis predicts, with remarkable precision, the abundances of hydrogen, helium-4 deuterium and lithium-7 that emerged from this brief epoch of cosmic alchemy. The predicted helium mass fraction is approximately 25%, the deuterium abundance approximately 2.5 parts per million, and the lithium-7 abundance at a level that has actually created its own small crisis. The lithium problem, where observations of ancient metal poor stars consistently find lithium abundances roughly 3 times lower than theory predicts, a discrepancy that remains unsolved but is not generally considered a fatal blow to the model. Large-scale structure formation, the growth of density fluctuations seeded in the inflationary epoch into the filaments, walls and voids of the cosmic web, is also described well by lambda CDM. The statistical properties of galaxy clustering, measured in surveys spanning billions of cubic light-years, match the theoretical predictions with a precision that constrains the matter power spectrum to the level of a few percent. The baryon acoustic oscillation scale, a preferred clustering distance of approximately 500 million light-years imprinted in the distribution of galaxies by the same acoustic physics that produced the CMB fluctuations, has been measured in galaxy surveys at multiple redshifts and agrees with lambda CDM predictions at the percent level. So when we say the standard model is under stress, we must be clear. It is not collapsing, it is cracking in specific places under the pressure of new data of a quality and precision that simply did not exist before Webb, before Planck, before the modern era of cosmological precision. The cracks are real, but they are cracks in an otherwise solid structure, fractures that demand explanation without demolishing the edifice. What makes the current situation historically interesting is the nature of the cracks. Previous anomalies in cosmological data, the peculiar velocity of galaxy clusters, the so-called cold spot in the CMB, the apparent excess of large-scale structure, have generally turned out, upon closer examination, to be statistical flukes, systematic errors, features that could be accommodated within lambda CDM with modest parameter adjustments. The Hubble tension is different. It has persisted and intensified as measurement precision improved. The little red dots are different. They are not a statistical fluctuation in survey data. They are individually confirmed objects whose properties are being characterized in detail by the best telescope ever built. There is a concept in the philosophy of science that Thomas Kuhn introduced in The Structure of Scientific Revolutions, the notion of anomalies accumulating at the periphery of a paradigm until the weight of anomalies becomes sufficient to trigger a scientific revolution, a paradigm shift, a replacement of the old model with a new one that accommodates the anomalies while retaining the successful predictions. The question that is now being asked in seminars and preprints and late-night conversations at conferences is whether we are in the anomaly accumulation phase that precedes such a shift, or whether the current anomalies will turn out, like so many before them, to be resolvable within the existing framework. The honest answer is, we do not know, and the people who are most credible when they say it are the ones who resist the temptation to declare that we do. What we can say is that the Rubies survey's discovery of approximately 10 times the expected number of massive quiescent galaxies at redshifts of 2 to 5, galaxies that have already shut down their star formation at an epoch when the universe was between 3 and 11 billion years old, implying that they formed their stars extremely rapidly and then became quiescent extremely early, is another line of evidence suggesting that the early universe was more efficient at building massive structures than lambda CDM predicts. The observation, published by the Rubies team in 2026, found quiescent galaxy number densities at high redshift that are 10 times higher than the model's prediction, not 2 times, not 3 times, 10 times. The specific little red dot known as Rubies UDS 154183, nicknamed the Cliff for the remarkable steepness of its Balmer break, is, in the assessment of the team that first characterized it, the clearest evidence yet that at least some little red dots are powered by a central ionizing source embedded in extraordinarily dense, absorbing gas, rather than by stellar populations. The spectral fits to the Cliff's observations favour an intrinsically red continuum rather than simple dust reddening, pointing toward either a super Eddington accreting massive black hole, one that is accreting matter faster than the Eddington limit nominally allows, or the presence of genuinely supermassive stars in a nuclear star cluster. Both possibilities would require the early universe to have formed objects of a kind not previously observed. The concept of super Eddington accretion deserves more attention because it is the mechanism that most theorists have identified as the most likely solution to the black hole mass problem. The Eddington limit is not a wall, it is a rate beyond which the radiation pressure from an accreting black hole's luminosity would, under standard conditions, prevent further infall of material. Standard conditions assumes an optically thin accretion geometry, one in which the photons generated by the accretion process can escape freely into space, exerting their momentum outward on the infalling material. If the accretion disk becomes geometrically thick, if the inflow of material is so rapid that the disk puffs up and becomes opaque, trapping the photons inside the disk long enough for them to be advected inward with the accreting gas before they can exert outward pressure, then the Eddington limit can be effectively bypassed. Super Eddington accretion flows of this kind are theoretically possible. They have been invoked to explain some ultraluminous X-ray sources in the nearby universe. But in the nearby universe, they involve stellar mass black holes accreting at modest absolute rates. In the early universe, if super Eddington accretion is genuinely operating in objects of the mass implied by little red dot spectra, the absolute mass accretion rates involved would exceed anything previously observed by orders of magnitude. Another observation that has emerged from the detailed spectroscopy of little red dots is the near-total absence of cold gas and cold dust in the most luminous examples. The Ruby's team published spectroscopic observations in 2025 showing that several of the brightest little red dots have far less hot and cold dust emission than either the AGN model or the star-forming galaxy model would predict. This deficit is diagnostic because both AGN and vigorously star-forming galaxies should be surrounded by dust heated to various temperatures by their central energy sources, warm dust heated by accretion disk radiation, cold dust heated by the interstellar radiation field. The fact that the dust is not there, or is present in quantities far below the model's predictions, either means that the objects have not had time to build up significant dust reservoirs, consistent with their extreme youth in a very young universe, or that whatever physical mechanism is powering them is of a nature fundamentally different from known AGN or star formation. One detail in the little red dot story that deserves careful attention is the object catalogued as Abell 2744 QSO1, described in 2025 work as a naked black hole, a little red dot, in which the central black hole appears to have essentially no surrounding galaxy. The stars that should accompany a supermassive black hole of its implied mass are absent, or present only at levels far below what the scaling relations between black hole mass and galaxy stellar mass, relations calibrated in the local universe across thousands of galaxies, would predict. If the central black hole mass is accurate, the ratio of black hole mass to stellar mass in Abell 2744 QSO1 exceeds the local ratio by a factor of roughly 1000. This is the black hole overmassiveness problem, and it is among the most precisely quantified anomalies in the entire little red dot dataset. Published analysis of the JWST OneCover program found that the supermassive black holes in little red dot galaxies are approximately 1,000 times larger relative to their host galaxies than black holes in the local universe. In all the galaxy surveys of the nearby universe, the mass of a central black hole is a fixed fraction, approximately 1/500th, of the total stellar mass of its host galaxy's bulge. This relationship holds across 7 orders of magnitude in galaxy mass, and is considered one of the tightest and most mysterious empirical regularities in extragalactic astronomy. In little red dots, it is violated by 3 orders of magnitude. One explanation for this is that we are seeing the beginning of the relationship. The black hole formed first, and the galaxy has not yet had time to build up its full stellar complement. The black hole seeds in this picture predate their host galaxies. They form first from primordial gas or from the collapse of supermassive population 3 stars, and only later does star formation proceed around them as the surrounding gas is enriched in metals and becomes capable of the more efficient cooling and fragmentation that characterizes modern star formation. This sequence, black hole before galaxy, is the inverse of what most pre-Webb models predicted, where galaxy formation was expected to precede or accompany black hole growth. If this picture is correct, then the little red dots are not young galaxies. They are young black holes, or quasi-stars, or supermassive primordial objects, caught in the epoch before their galaxies exist in any meaningful sense. They are the precursors to the structures that would one day become the centers of normal galaxies. They are seeds, and that, if true, would require us to revise in fundamental ways our understanding of what came first in the universe, not in any metaphysical or philosophical sense, but in the rigorous empirical sense of which type of cosmic structure preceded which, and by what physical process the universe assembled itself from the uniform plasma of the Big Bang into the richly structured cosmos we inhabit today. The question of what came first, the galaxy or the black hole at its heart, has been one of the deepest open questions in extragalactic astronomy for 2 decades. The little red dots may be providing the answer. The black hole came first, and it came in a form nobody predicted. there remains one more line of evidence that ties the little red dot puzzle to the broader crisis in cosmology in a way that has received less public attention than it deserves, but that strikes several theorists as potentially the most significant connection of all. It concerns the cosmic microwave background and the small-scale structure of the universe at the epoch when the little red dots were shining, cosmological simulations that attempt to include the effects of early, rapid black hole formation and super Eddington accretion on the surrounding intergalactic medium find that these processes would have produced significant quantities of energetic radiation, not just the X-rays that the black holes are apparently trapping within their dense gaseous envelopes, but also ionizing ultraviolet and extreme ultraviolet photons that could leak out and contribute to the reionization of the universe. Cosmic reionization, the process by which the neutral hydrogen fog that filled the universe in its first billion years was progressively ionized by the first luminous sources, is one of the key transitional events in cosmic history, and its history is partially encoded in the cosmic microwave background and in the spectra of the most distant quasars. If little red dots contributed significantly to reionization, their abundance might explain some of the anomalies in reionization history that had previously been attributed to galaxies alone. This is speculative, but it illustrates the extent to which a single class of newly discovered objects, the little red dots, pulls on threads that connect to almost every major open question in cosmology simultaneously. They are implicated in questions of black hole formation, galaxy formation, the Hubble tension, cosmic reionization, and the nature of the first stars. They are not a side note. They are potentially a central chapter. Science does not resolve its deepest mysteries with existing tools. It builds new ones. The little red dot problem and the Hubble tension are, at their core, measurement challenges that demand new capabilities, deeper surveys, longer wavelength coverage, more objects spectroscopically confirmed, better characterization of the dust and gas environments that make existing measurements uncertain, and entirely new observational modalities that approach the same physical questions from independent directions. The James Webb Space Telescope, extraordinary as it is, was not designed to answer questions that were not yet known to exist when its science requirements were written in the 1990s. It was designed, among other goals, to study the first galaxies, and it is doing so with a completeness and a richness that surpasses every expectation. But the specific spectroscopic capabilities needed to fully characterize little red dots, to determine with certainty whether their central engines are accreting black holes, quasi-stars, or supermassive population 3 stars, require measurements in wavelength ranges and at signal-to-noise levels that push against the limits of what Webb can deliver, even in very long exposures. The next instrument to make significant contributions to this problem will almost certainly be the Nancy Grace Roman Space Telescope, scheduled for launch no earlier than late 2026. Roman is designed specifically for wide-field near-infrared imaging and spectroscopy, and its 4-meter mirror, the same aperture as the Hubble Space Telescope's primary mirror, coupled with a detector array 200 times larger than Hubble's, will enable it to survey areas of sky roughly 100 times larger than Webb's widest field of view. For the little red dot problem, this is important because the current sample of confirmed objects is limited not by the sensitivity of Webb, but by the volume of sky surveyed. To characterize the abundance and distribution of little red dots with the statistical precision needed to test theoretical models rigorously, astronomers need to count them across sky areas large enough to sample the large-scale structure of the early universe. Roman will provide that area. On the ground, the next generation of extremely large telescopes, the European Extremely Large Telescope in Chile's Atacama Desert, with its 39.3-meter primary mirror, scheduled for first science operations in 2028. The 30-meter telescope, if and when it achieves its contested construction site, and the giant Magellan telescope with its effective 24 5-meter aperture will bring collecting areas that exceed Webb's by factors of 15 to 35. On the ground, atmospheric turbulence limits angular resolution without adaptive optics correction, but the sheer collecting area of these instruments will allow spectra of little red dots and distant quasars to be obtained at far higher signal-to-noise ratios than Webb can achieve, enabling the detailed chemical abundance analyses, precise velocity dispersions, and resolved spatial structure measurements that would definitively distinguish between the competing theoretical models. For the Hubble tension specifically, the most promising near-term approach is the expansion of time delay cosmography, the method of measuring the expansion rate directly from the time delays between multiply-imaged quasars or supernovae lensed by foreground galaxy clusters. Brenda Fry's program using Webb to monitor lensed supernovae in massive galaxy clusters, including the striking 3-image system in the cluster G165 discovered in 2024, which yielded an independent Hubble constant measurement of 75.4 kilometers per second per megaparsec, represents a route to the Hubble constant that is genuinely independent of the distance ladder. It does not use Cepheids, TRGB stars, or Type Ia supernovae as calibrators. It uses geometry, the angular positions of multiple images, the measured time delays between them, and a gravitational lens model. As the sample of lensed systems grows, Fry's program is monitoring 7 clusters, with ambitions to expand. The statistical power of this method will increase, and its uncertainties will shrink. Gravitational wave observations offer another route: the detection of gravitational waves from binary neutron star mergers. Sources whose absolute luminosity distance can be calculated directly from the amplitude and frequency evolution of the wave without any reference to a distance ladder provides a measurement of the Hubble constant that is in principle entirely free of the systematic errors that have plagued traditional methods. The 2017 event GW170817, the first binary neutron star merger detected by LIGO, produced a Hubble constant estimate of approximately 70 kilometers per second per megaparsec, sitting tantalizingly between the two competing measurements, with a statistical uncertainty of 12% that made it non-discriminating. As gravitational wave detections accumulate over the next decade, the LIGO-Virgo-Cagra network expects to detect tens to hundreds of such events per year at design sensitivity. The combined gravitational wave Hubble constant will converge toward a precision that could definitively adjudicate the tension. Most speculatively, but perhaps most consequentially, a next-generation cosmic microwave background experiment, CMBS-4, a ground-based array of 500 00 superconducting detector elements planned for deployment at the South Pole and in Chile, would measure the CMB temperature and polarization fluctuations with a sensitivity 10 times greater than Planck, probing the physics of the early universe at energy scales and angular resolutions that could distinguish between the various early dark energy models and other new physics proposals that theorists have invoked to resolve the tension. If early dark energy contributed significantly to the expansion history, CMBS-4 should detect its signature in the form of specific patterns in the CMB polarization power spectrum that lambda CDM without early dark energy would not produce. Whether any of these instruments will deliver a clean, unambiguous answer is not guaranteed. The history of the Hubble constant, a parameter that has been continuously measured for nearly a century by increasingly sophisticated methods without converging to a consensus value, suggests that the universe will not yield its secrets without a fight. But the trajectory of capability is clear. Over the next decade, astronomers will have tools that make Webb look, in some respects, like a prototype. The little red dots, meanwhile, will be targeted by every new instrument that comes online. Their spectra will be dissected with greater precision, their morphologies resolved at finer scales, their variability monitored with greater temporal coverage. The sample of 341 confirmed objects will grow to thousands, and within those thousands, the diversity of individual objects will either reveal a unified physical origin or expose a population of genuinely distinct phenomena that happen to look similar at Webb's current resolution. In either case, the answer will change our picture of the first billion years of cosmic time. The question of whether little red dots are black holes in cocoons, quasi-stars, or the first stars of the universe will not be resolved by a single observation or a single paper. It will be resolved by the accumulation of evidence, the refinement of models, the failure of explanations to survive detailed prediction testing, and ultimately by the convergence of independent lines of inquiry toward a picture that explains everything simultaneously. That process is already underway. It is happening faster, with better data, than anything comparable in the history of cosmology, and underneath it all, there persists a question that no planned instrument directly addresses. If the standard model of cosmology is incomplete, if the universe is expanding faster than lambda-CDM predicts, and building massive objects faster than lambda-CDM predicts, and doing so in forms that lambda-CDM does not anticipate, what does the new model look like? What is the missing ingredient? What do we need to add to our equations to make the universe we observe match the universe we calculate? The history of physics suggests that the answer, when it comes, will be both satisfying and unexpected. Quantum mechanics resolved the ultraviolet catastrophe in blackbody radiation by proposing that energy is quantized, a proposal so radical that even Planck, who made it, did not initially believe it was physically real. Special relativity resolved the incompatibility of Newtonian mechanics with Maxwell's electromagnetism by proposing that time itself is relative. Dark energy was discovered not by theorists who predicted it, but by observers who measured something they did not expect. The history of physics is a history of surprising resolutions to persistent paradoxes, and there is no particular reason to believe that the resolution of the Hubble tension or the little red dot problem will be less surprising than its predecessors. What we can say with confidence is this: the James Webb Space Telescope has already, in 3 years of operations, done something that no previous telescope has managed to do at cosmological scales. It has produced anomalies that are quantitatively specific enough, statistically robust enough, and theoretically disruptive enough to force the cosmological community to take seriously the possibility that the standard model is not just incomplete in its parameter values, but incomplete in its physical content. The anomalies might in the end be resolved within lambda-CDM by mechanisms we have not yet identified, but they might not, and the honest reckoning with that possibility is what makes this moment in the history of astronomy so genuinely consequential. We are not, as some popular accounts have suggested, watching the standard model collapse. We are watching it being tested with unprecedented rigour by an instrument of unprecedented power, and we are discovering, for the first time, exactly where its predictions fail to match reality. Those failures are not a crisis, they are an invitation. The universe is, in the most specific and technical sense possible, showing us where to look next. There is something that no equation captures and no telescope resolves, and it is the feeling of standing at the edge of what is known and looking out over what is not. The little red dots are out there right now, scattered across the high redshift universe, blazing in the infrared with the light of 1 billion suns, compressed into a space smaller than the distance between the Sun and its nearest stellar neighbours, shedding photons that left them when the universe was 500 or 600 or 700 million years old, and that have been travelling through expanding space ever since, stretching as they went from ultraviolet to visible to infrared, until they finally struck the detectors of a gold-coated mirror orbiting a small planet in an unremarkable galaxy in one of billions of galactic filaments, and we looked at them and said, "This is wrong. This is not what we expected. This does not fit." What we do with that not fitting is everything. The temptation when a model is stressed is to reach for the simplest revision that makes the anomaly go away. Add a parameter here, adjust an assumption there, and the curve bends back toward the data. This can be the right move, but the deepest advances in physics have come not from patching anomalies, but from listening to them. from taking the not fitting seriously enough to ask not how do we fix the model, but what is the anomaly trying to tell us about reality? The little red dots, seen from this perspective, are not a problem to be solved. They are a message. From the first billion years of the universe, from a cosmic epoch we have never before been able to observe in this detail, from objects that do not fit our categories and do not obey our predictions, comes a persistent, repeated, statistically robust signal. You do not know what we are, and you need to find out. The same is true of the Hubble tension. 5 standard deviations, persisting through every improvement in measurement technique, growing rather than shrinking as the data quality improves. This is not noise. This is the universe insisting, with increasing volume, that our best model of cosmic evolution is missing something in its foundational physics. Something that has been operating since the beginning, shaping the expansion history of all space, and that we have not yet found the conceptual vocabulary to describe. Human beings have a relationship with mystery that is, I think, one of the more admirable features of our species. We do not merely tolerate not knowing, we are drawn to it. We build machines the size of tennis courts, fold them inside rockets, and send them 1.5 million kilometers into space, not because we know what we will find, but precisely because we do not. The 344 deployment steps of the James Webb Space Telescope are, in some sense, a monument to that impulse. A willingness to bet everything on the possibility that the universe, seen clearly enough, will show us something worth seeing. It has. And what it has shown us is not a completed picture, but a deeper puzzle. Not an answer, but a better question. The little red dots do not tell us what the early universe was. They tell us that the early universe was stranger, richer, and more structurally complex than any model predicted. The Hubble tension does not tell us what the correct expansion rate is. It tells us that our 2 most carefully developed methods of measuring the universe's expansion do not agree, and that the disagreement points toward physics we have not yet written down. There is a kind of cosmological humility that these discoveries demand, and it is not the humility of defeat. It is the humility of realizing that the universe is bigger, more complex, and more surprising than any framework a human civilization has managed to construct in the brief time it has been asking these questions. The lambda CDM model is not wrong in the way that a clock without batteries is wrong. It is wrong in the way that Newtonian mechanics was wrong before Einstein. Correct in its domain of application, silent about a deeper reality that it was not built to see. Whatever that deeper reality is, whatever the new physics looks like when it is eventually written down, whatever the dark sector contains that we have not yet discovered, whatever the little red dots turn out to be, it will not arrive fully formed from a single observation or a single paper. It will arrive the way all great scientific advances arrive, haltingly, contested, accompanied by the noise of competing interpretations and the occasional embarrassing error, and recognized as a breakthrough only in retrospect, when the picture resolves from static into clarity. The people who will see that clarity are younger than anyone now working on this problem. They will have access to instruments that do not yet exist, computational resources that have not yet been built, and theoretical frameworks that have not yet been proposed. They will look back at the James Webb Space Telescope as we look back at the telescopes of Galileo, not with condescension, but with recognition. That was the moment the light began to arrive. That was when the universe first showed us what it was hiding. We are, right now, living in that moment. It does not feel like a revolution. It feels like confusion, like contested papers and unresolved anomalies and rival teams disagreeing at conferences. But that is exactly what a revolution feels like from the inside. The turning is invisible until you have turned. In a patch of infrared sky, smaller than a grain of sand held at arm's length, 341 confirmed, little red dots are waiting to be understood. They are patient. They have been there for 13 billion years. The question is whether we are patient enough, and curious enough, and honest enough about what we do not know to understand them. I believe we are. That question, though, what they are, what they mean, what the universe was doing in its first billion years that our best models failed to predict? That question has no final answer yet. It sits at the edge of what we know, casting light forward into what we do not, illuminating not a destination but a direction. And perhaps that is all science ever gives us, not the last word, the next word, the word that carries the question further into the hands of whoever comes next.